Welcome back, everybody. Just a quick note. I'm still in the process of grading the exams, at least the questions that need my input. So those should be done by tonight. Got a few more from your class to do. So those will be done. Okay. Any questions right now? Everything? Any questions about anything? No? Okay, I will continue with chapter 7. We were on slide number 16. Okay, now we're talking about the chemical bond. The thing to remember about this chemical bond business is this: there's only two types of chemical bonds. One is called an ionic bond, and that is made up from a combination of a metal and a non-metal. And then the other one is a covalent / molecular bond. They use that term. You see that term used often, both of those. And that is a combination of a metal, non-metal and a non-metal. Okay. And so those two things are important to know. In other words, you have to go to the periodic table when you have a combination of two compounds and determine whether it's ionic or covalent, and you have to know which ones are metals and which ones are not. Okay, and that little stair step of the periodic table helps you out, because to the left of the stair step are the metals. Now, the thing to remember about that stair step, let me show you that, is that hydrogen, look at hydrogen's way out there, element number 1. That is not a metal, okay? It is placed there because it shares what everyone else does in that same group, and that is they have one valence electron. Hydrogen's the first element, has only got one valence electron, so it's put there because of that, but it's not a metal. There's a stair step to the left are classified as metals, and to the right of those are the non-metals, okay? And once we determine metal, non-metals, that now introduces us to a variety of different properties of these chemicals. And so it's quite crucial to be able to distinguish whether you're working with an ionic compound or a covalent compound. And then further down the road, you're going to learn that the covalent compounds, they themselves are subclassified as either what we call polar or non-polar. Another way of saying that is, do they have properties of water-like properties versus oil-like properties? And that affects a lot of the solubility of material and so forth. And anyway, so we got to learn about metals, non-metals. Now, this step here is called Lewis dot structures. Very straightforward, nothing complicated. It only applies to the 8 elements, Roman numeral 1 or I, all the way to 8. Okay, why is that? Because those are the only elements that we know for sure how many valence electrons they have. So depending on the group that they're in, tells us how many valence electrons they have, and we can draw the Lewis dot structure for the atoms very quickly. If, for example, you're asked to draw the Lewis dot structure for, let's say, sodium. So we write the symbol sodium, okay? And then the next thing we do is we go look for it on the periodic table, and we'll find it to be in group 1. That means that there's one valence electron. So the Lewis dot structures only have to deal with the valence electron. So we simply make a dot, and that's it. Lewis dot structure for sodium is sodium, the symbol, and a dot. And that would be true for all of the elements, including hydrogen, in group 1. So group 2, let's pick magnesium. Okay, and then I put 2 dots. Okay, now when you put these dots, the format, if you will, is as follows. Think of it as a box. Okay, so SY represents the symbol, and we got a box here. Okay, and so when we place dots put them, start them anywhere you want, either top, bottom, left, or right. Put one dot. And if you got to add a second dot, we don't put it on the same line. We go to the side or to the left side. Either way, whichever direction you want is fine. And if we got to put a third dot for 3 valence electrons, we put a dot down at the bottom. And then fourth one all the way around the horn, so to speak, okay? Now, if we need to go to the 5th dot, then we go and we fill up one of the lines, one of the sides of the box to 2. That's the maximum we can put in. And we keep, if we need one more, we keep going. Okay, and such time that we have 8 electrons, which is the maximum number of electrons that you have. 8, octet, very important rule. Okay, so that would be representative of the Lewis dot structure for any of the normal gases, because 8 electrons around it. Now, whether you start up here and go around, or you go in the other direction, makes no difference. Totally up to you. Whether I start at the bottom, left, right, or top of the box, totally up to you. Just don't put them together. So magnesium, based on the format, would not be written in like this. This is not the format for the Lewis dot structure for magnesium. Okay, because as you know, when we talk about the valence electrons, we filled them up, you know, box per box. Okay, so if we had 3 p orbitals, we fill up each one first before we went around and filled up the first box. So keep that in mind. Clear this up. So this is pretty straightforward. Identify the valence electrons. So remember, that's the group number, the group A elements. Okay, that tells you how many valence electrons you have. Very straightforward. And then that's it. So if, for example, they ask you to do the Lewis dot structures, let's say for the atoms of potassium, oxygen, silicon, magnesium, and iodine. Well, we simply first identify the group that is in. Potassium is in group 1A. Okay, oxygen is in group 6A. Silicon is in group 4A. Magnesium is in 2A. And iodine is in 7A. Okay, and it basically says I got 1 electron, valence electron, 6 for oxygen, 4 for silicon, 2 for magnesium, and 7 for iodine. So once we identify that, it's a matter of putting the dots in there, and you have something as follows. Okay, so those represent the Lewis dot structures of atoms, individual atoms. Had nothing to do with compounds, molecules. Okay, because the next step, we're actually going to be dealing with structures. Okay, you'll be given a formula. Okay, and from that information, you're going to find out how many valence electrons each atom that brings to the compound exists. You add them all up. That tells you how many total valence electrons you have based on the elements of that compound. And then that tells you how many bonds you have. And from that information, we're going to draw a structure. Now here, we also need to use the shapes table. So if you've not printed that for yourself, you may want to do that, because once we find a structure, and we're going to do some examples, that gives us what's called a general formula. And the general formula consists of 3 letters. Okay, and I can't overemphasize this. It is a general formula. It's not specific to anything. And it consists of 3 letters. First one is A, okay? A represents the center atom of a compound. You'll be told what the central atom is. What that means is you got a central atom, and then whatever follows is bonded to the central atom. Okay, so A will always be 1. They won't have more than 1. B represents, in general terms, how many atoms are bonded to A, the central atom. Okay, we don't care about any other atoms. We just care about the central atom. How many are bonded to that? And hence we have an X there because that number could be a 1, could be 2, could be 3, could be 4. Maximum is 4. Well, for us, maximum is 4. Okay. The next letter, which is an E, represents what we call lone pair of electrons on the central atom. Now, what do we mean by lone pair? Okay, let's take the structure for water, H2O. And we're going to go through the exercise and how we came up with this. That line that I wrote between the oxygen and the hydrogen is a bond. There's 2 electrons on that, okay? Also on oxygen, I put 2 dots, which I can write as 2 dots, or I tend to prefer like a hyphen, a line sign. Those 2 symbols are the same thing, okay? So that line represents 2 electrons or 2 dots. Notice that there are 2 pairs of these electrons, 2 pairs, because these electrons come in pairs, whether they're bonded or non-bonded. We've got 2 pairs that are non-bonded, okay? And so for water, it would have 2 bonded pair and 2 non-bonded or lone pair. Okay. And that's what E is. And I put a Y here because it can vary. It could be 1, could be 2. Okay. And what this says is how many electrons that are lone pair that are not bonded to anything exist on the central atom, period. Okay. We don't care about any other atoms. We just want to know about the central atom, denoted in general terms of A. Once we develop the general formula, then that's where we use the shapes table, because we use the general formula, and I'll tell you how we did this, but the central formula, we're going to go through it. For water is AB2E2. A represents oxygen. B represents the 2 hydrogens. Now, they don't have to be the same element. They could, atom, they could be different or the same. It doesn't make any difference. They just know how many B's are attached to A. So in this case, there's 2. And then oxygen has 2 lone pairs. So the general formula for water would be AB2E2. Then we use in the table, we search for AB2E2, and there it is down at the bottom. Here's the general formula, okay? Here is a general geometric shape for water. These oxygens in the center, and then we get the hydrogens over here, and then it has the 2 lone pairs. And it looks like this is lobe. It doesn't have a lobe. That those 2 dots kind of represent the orbit of those 2 electrons. Okay, so that's why you see this pear shape there, just to represent a lobe. That's the geometry, and that is the name for that geometry. That geometry has a specific name. And then it also gives you a bond angle, and that is the bond angle between the 2 hydrogens. You can see this have this number less than 104. Now, the reason they do that is because the most common structure for majority of the compounds are this AB4, where we have this tetrahedral, and we have this 109.5 bond angle here. Because remember, each line there represents electrons, and those electrons are negative charge. And so if those bonds were like springs and we have 4 springs, well, they would adjust themselves to repel from each other in that configuration, that 3-dimensional configuration that we call tetrahedral. And that bond angle is the maximum angle that these bonds push away from each other, so that everybody has been separated, given the shape that they have, okay? And that is a kind of a reference point of that bond angle, 109.5. So you can see that water has an angle much less than 109. And that is because those crazy lone pairs, they're negative. Remember, they're not bonded. They're negative charge, and they repel each other. all four of them repel each other, resulting in this bond angle being much less. Okay. And those kind of things really put a big factor on properties of chemicals. Lone pairs can affect the properties of the chemicals just because of the geometry of the compound. All right, so let's go back. So what do? We get determine the total number of valence electrons that every atom brings to the table, if you will. All right, let's take the structure for H2O. You're given it. Now, you'll be always told what the central atom is. Now, that by default, I said before, normally a central atom is written first, symbol that is, and then followed by whatever is bonded to the central atom. But there are exceptions to the rule. Water is one of them. In this case, they write what is bonded to oxygen first, then they write the central atom. Well, normally it will be denoted by either an underscore or it will be bold, okay? So that's telling you that oxygen is a central atom, and those two hydrogens are not hydrogen gas, but hydrogen atoms that are bonded to the central atom. So we add up the total number of valence electrons. So we got to determine which atoms do we have. Well, obviously we got hydrogen, okay? And there are two of them. And those two, each one has an atomic weight of, they have one valence electron apiece, right? Because they are in group one. So there's a total of 2 valence electrons being brought to the table, to the chemical by hydrogen. If we look at oxygen, there's only one of them, okay? We have to account for the total number of atoms, and oxygen is in group 6 of the periodic table. So that is 6 valence electrons. That means it brings 6 to the table. So we have a total of 8 valence electrons, okay? That is what you got to work with. We cannot magically add more if we need them or take out if we don't need them, okay? That's 8. You got to make 8 work with respect to your overall structure, okay? Now, what I tend to do is I take that 8, that number is always going to be divisible by 2. So I divide it by 2, and that tells me that I have 4 pair of electrons to work with. And that's easy for me because I just draw lines and that represents a pair, okay? So we counted up the valence electrons from all the atoms. We have a total amount. In this case, we got 8, which is a fairly small amount, but you can go up high, 32 valence electrons and so forth. Then I divide that by 2 to give me a number of so it's 4 pairs of electrons that I got to work with. I cannot remove, I cannot add any more. 2 things to remember when drawing these Lewis dot structures. We need to fulfill the octet, okay? The driving force, as we spoke, is to maintain 8 electrons around that element, with the exception of hydrogen. Hydrogen will always have only 2. It doesn't have an octet rule, it has a duet rule. And so that implies something fairly straightforward now, that hydrogen can only make 1 bond. So you will not see hydrogen with more than 1 bond in any compound, okay? If you do, it's incorrect. All right, so the other atoms, when we put them together, have to maintain 8 valence electrons. Now, this is done sometimes just by default, depending on how many valence electrons you calculated. It falls into place and everybody's happy. Occasionally you don't, you're short. And what happens, you have to start making double bonds and triple bonds. Remember the bonds we talked about for covalent compounds? There's a single bond, a triple bond, double bond, and a triple bond. And so if you come up short as far as making sure the octet is fulfilled for every of the atoms, then we start sharing electrons from one atom with the other atom. When we start creating double bonds and triple bonds as needed, such that everybody now has octet electrons around it. They're being shared, but they have an octet. All right, so now, given that the fact, like I told you, that oxygen's the central atom, I can write oxygen in the middle. And so that tells you that hydrogen is bonded to the oxygen. So we can draw a line and connect a hydrogen, okay? 2 lines, because we have 2 hydrogens. So those 2 lines represent a pair. We had 4 pairs to work with. I can subtract 2. I got 2 pair left. I got to put them someplace, okay? Well, as I stated, I cannot put them on hydrogen because hydrogen has a duet. That bond between the oxygen and the hydrogen is being shared. So it can be counted toward the oxygen and it can be counted toward the hydrogen. And so if you count the number of electrons around hydrogen just by itself, we got a single bond, got 2 electrons, it's happy. We count the electrons on the other hydrogen, same thing, it's happy. So we can't add any more onto the hydrogens. The only place we can put them is in the central atom, and I draw a line, or if you want, you can put 2 dots there. Whichever one's, both, what I just did is both is the same. Now I keep track of my pairs, right? I still have 4 pairs. I got 2 that are not bonded and 2 that are bonded. Remember, because I got 4 to work with. I got to work with that number. And so that is the structure there, okay? Now, geometry, what I do is we say, okay, A is always there, that represents hydrogen. B is represented by the 2 hydrogens, excuse me. A is the oxygen, B is the hydrogen, okay? And there's 2 of them, so I put a subscript 2. There are lone pairs on the oxygen, so therefore I got an E. And there's a subscript 2. So there is a general formula I was showing you earlier. That's been created. Now I can go to the shapes table, and that will give me the shape and then the name of the shape and the bond angle. Okay? All right. We're going to do some more examples here, so you'll get the hang of it. So we add up the total number of valence electrons, okay? We surround the central atom with the other atoms, whatever they were, whatever they are. We draw a single bond between them, okay? Central atom's always going to be underlined or be put in bold. And then we start checking to make sure that the octet rule is fulfilled in all the atoms, with the exception of hydrogen, which has a duet rule, right? All along the line, as I'm making bonds and so forth, keep track of the pairs that you have to work with, or the total number of valence electrons, whichever one you want to use, because that is the number that I need to work with and need to make it work, okay? And then identify on the central atom bonding pairs or bonding electrons, and then identify which ones are the lone. The reason we need to make sure it's lone, because then we go find the central atom, and that determines whether we get an E or not, okay? Now, if we have whatever amount of valence electrons or pairs, and the octet is not being fulfilled, then we start creating single and double bonds as needed until such time that the octet is fulfilled for all the atoms involved, okay? Let's try that. Where we did water, we'll do this when we get next slide, you'll see some examples and we'll break it down. So we added up the valence electrons for water, as I did earlier. I got 2 hydrogens and oxygen has 6. I got 8 valence electrons, or 4 pair, okay? I write down oxygen, and I write 2 lines for the hydrogen. That takes care of the bonds of hydrogen and oxygen. And then I got 2 more, I got to put them someplace, and by default, they go onto the oxygen because they can't go on the hydrogen, because the hydrogen can only handle a maximum of 2 electrons, okay? And as you go along, you do this, double check your number of pairs that you calculate to have, okay? If you end up with extra electrons and the octet is all full, then maybe you miscounted the number of valence electrons. So go back and check that. If you come up with a shorthand and you can't make any more double and triple bonds, then again, go check your math with respect to the valence electrons, because that's probably the culprit, okay? Remember, single bonds are single, double, triple. There's no such thing as quadruple bonds, just single, double, and triple. Okay, so there's the structure of H2O like we did earlier. All right, well, let's try a couple, okay? So we have this compound, okay? And I know you don't know what it is, that's okay, you know, but you got hydrogen, carbon, and nitrogen involved there, okay? And if you want to know, that's hydrogen cyanide, poisonous gas. All right, first things first, we want to count the number of valence electrons. Identify the central atom, I should say, first thing first, and it's underscored. Okay, so carbon is a central atom, meaning that the nitrogen and the hydrogen are bonded to the central atom. So let's figure out the number of valence electrons. So we have hydrogen, and there's only one of those, and it has one valence electron, so it brings to the table one valence electron. Now, who can tell me how many valence electrons? We only got one of them. How many valence electrons does carbon have? Who can tell me that? How many valence electrons does carbon have? Okay, carbon's element number 6. Anybody want to try it out?
Four?
You got it. Okay. And how did you know it was 4? That is correct. How did you know it was 4?
Is it because each of the atoms has one valence electron?
Ooh, you broke up a little bit. How did you determine 4?
Because each of the atoms has one valence electron?
Not for carbon.
Oh.
But your answer's right, but I don't know where you got it, because what group is carbon in? Who can tell me what group carbon's in?
It's in group 4.
It's in group 4. Check your periodic table. Okay, it's in group 4. So everybody in group 4 has 4 valence electrons. And there's one of them, so therefore the total number of valence electrons that carbon brings to this structure is 4. Okay, what about nitrogen? We got 1 nitrogen. How many valence electrons does nitrogen have? Right next to carbon. What do you think, Larsa? Do you know how many valence electrons nitrogen has?
Not quite. I'm not sure.
Okay. Well, if you got your periodic table, find nitrogen. It's number 7, and then look up on top, see what group number it's in. It should be Roman numeral V for 5, and that means nitrogen has 5 valence electrons. Okay, and so the total valence electrons that you have is 10 total. This is the number that you work with. That is what you got. You can't take them out. You can't add more. You got to make 10 work. Okay. Now, you should get a number that's divisible by 2. So if you end up with 11 or 9, something may have happened. Okay. So this represents to me 5 pair. And like I said, I like to work with the pair because I just simply draw a line that's a pair, rather than having to do 2 dots, a lot of dots. Here, not so much, but some compounds have a lot of dots and you might lose track of what's what. And all right, so let's do the structure, see what we got. We know that carbon is the central atom, and that means that the nitrogen and the hydrogen are bonded to the central atom. So we can simply draw a line and connect nitrogen. And then we can go and connect another line and connect hydrogen, okay? So you see that took care of 2 pairs. So I can subtract those 2 pairs to the 5 that I got to work with. So now I got 5 pair of electrons that I need to work with. Someplace, somehow I got to put them. Now, I can't put them on hydrogen, remember? Because hydrogen is a duet. So a lot of students have a challenge with this part. That line right there represents a bond. And then in that bond is 2 electrons. And those 2 electrons are being shared by hydrogen and carbon, okay? They're being shared by hydrogen and carbon, just like right on the other side, that line represents 2 electrons that are being shared by carbon and nitrogen. It's a single bond, okay? Now, that means I can count those 2 electrons for both the hydrogen and the carbon when I start looking at the octet rule or the duet. So there's 2 electrons in that bond. I cannot add any more to hydrogen. Why? Because hydrogen's rule is 2, duet. I can't add any more. So whatever I got left over can't go to the hydrogen, well, actually will go to the carbon and or the nitrogen. Now, which one you select, totally up to you. I like, if I have some compound like this or anyone, I like to put whatever pairs I have on the atoms outside and work my way around the hat, so to speak. So I'm going to put them all what's left on the nitrogen. And I got 3 left, right? So I go 1, 2, and 3. And that takes care of my electron pair, okay? Double check, because you double check along the road, because sometimes these lines disappear if you're not checking. So right now I have five bonds. 2 of them, one of them is bonded with the hydrogen and the carbon. The other one is bonded with the carbon and the nitrogen. And then there's 3 of them that are not bonded around the nitrogen, okay? So now, how many electrons can you guys see that are around nitrogen right now as written like that? How many electrons are around nitrogen? You can tell me either as total number or as pairs, either way. Well, how many lines are there around nitrogen, including the bond?
Is there 8?
You got it, okay? There's 1, 2, 3, and then the 4th one right there. 4 lines. Each line represents 2 electrons, which means I got 8 electrons around nitrogen, which means that nitrogen's happy. You know, as they use the term for, you know, the octet, they're happy. Yeah, I'll stick with the term happy. To me, nitrogen stable because it's got 8 electrons around it. What about carbon? How many electrons do you guys see around carbon the way it's written right there? Well, how many bonds are around carbon right now? There's only 2. There's 1 bond with the hydrogen on the left, and there's 1 bond with the nitrogen on the right. Each bond represents 2 electrons, so I got a total of 4 electrons around carbon right now, the way it's written, which violates the octet rule because it needs 8, okay? Nitrogen's happy, hydrogen's happy, carbon is not, okay? I cannot magically add any more electrons because I have a total of 10 electrons or 5 pair to work with. That's what I got to work with. I can't add any more. That's it. And so what I do now, I start creating single and double bonds as needed. So I borrow electrons from Paul to share with Peter, so to speak, okay? And so I can take any one of these on the nitrogen, and I'm just gonna draw an arrow and say, okay, I'm gonna put that right here and make a double bond. So now I got carbon, double bond, nitrogen. Now I didn't lose the other lines. I'm gonna keep them there so you can see them. And then I have a hydrogen, okay? Now, nitrogen is still happy. Nitrogen still has 8 electrons around it. We got 2 that are not bonded and 2 that are bonded, okay? But carbon, how many electrons do you see around carbon right now as written for the second diagram I wrote? How many electrons are on carbon right now?
6.
6. So again, we have no octet. Nitrogen's good, hydrogen's good. So what do? We create a bond. And this time we're gonna make a triple bond. I'm gonna pick this pair and draw another arrow. And now I created a triple bond right here. Okay. Okay, now, as a check, notice I've taken 3 steps here. Follow my bonds, make sure I don't violate that 5 or lose them along the way. I still have 5 bonds all the way at the end. One of them is bonded with hydrogen. I got a triple bond between the carbon and nitrogen, and I got a lone pair on the nitrogen. I have 5 pairs, so I've not violated my initial 5 pair that I calculated, okay? Now I check the octet. Nitrogen still maintains 8, but now carbon has 8. That triple bond is shared between the nitrogen and the carbon. So they count in both directions. So, if I were to draw like a little jagged line here so I can see, to the right of the jagged line, I got 8 electrons. To the left of the jagged line, I got 8 electrons on the carbon, okay? See how that works? So everybody there is happy, stable, 8 electrons around it, or 2 for hydrogen, and is good to go. So that is, let me erase this, I'll rewrite it. So that is the formula that we come up with, okay? Now, next step, create the general formula. So obviously we have A, always all the time there. B, what do you guys think B should be? The subscript, I should say, for B. We're making the general formula. What should be, how many atoms are bonded around the central atom?
2.
Exactly, 2. Again, it doesn't make a difference if they're the same or different. There's two atoms bonded to the central atom. So we got a subscript 2. Now, do we have an E here? No, we don't. We don't have any lone pair on the central atom. Okay. Yes, there is a lone pair on the nitrogen, but that is not the central atom. We only care about the central atom. So our general formula is AB2, okay? With that information, then we go to the periodic shapes table, and we look for AB2. And AB2 is right there. So this is what we came up with in the other slide. And that's AB2. That's the general formula. That means that the general geometry is in the second column. This is carbon in the middle here. That would be nitrogen, and that would be hydrogen. The bond angle that is between the 2 moieties that carbon is bonded to is 180 degrees. Okay, so from here to here, we got a bond angle of 180 degrees. And it has a particular name. It has a linear configuration, okay? The name of the shape that it has. And so that's how we come up with this geometry and the name and the bond angle by first adding up all of the valence electrons from all of the atoms involved, okay? And then identifying who's the central atom, and then start making double or triple bonds or single bonds, whatever you need to get the octet fulfilled, okay? And so that's the formula, which is exactly the same formula we just created. And we also know the geometry and so forth. Now, the next one's a little bit more challenging, but not undoable. All right, so we have this species here, and this is a what in general terms is called the floral hydrocarbon. A lot of freons and stuff use hydrocarbons that have fluorine or fluoride attached to it, and they're bad guys too because they get up to the ozone layer up on top in the atmosphere that protects us from UV lights and destroys it. All right, so we got one carbon, okay? Everybody agree we got one carbon, right? Look at this, the carbon is underscored. So we got the central atom is carbon and the hydrogen and the fluorides are bonded around the carbon. We got one carbon. How many valence electrons come from carbon? We just did it.
4.
4, thank you. All right, so I got 4 valence electrons coming for carbon. All right, we got one hydrogen, like we did before, one hydrogen. Now I know this might sound redundant, I'm writing all these out, but this is just to keep track. I have a little grocery list of things I'm keeping track of. Once you become familiar with this, you don't have to do this. But again, this is my approach of attacking it with a systematic steps. And finally, the fluorides, we have 7 of them. And how many valence electrons does fluorine have? Did I say 7 of them? Boy, it's been a long day. You know what I just gave you? You got 3 fluorines. How many valence electrons does it have? 7. I did my little dyslexia thing. I flipped it over my head. There's 7 valence electrons. How do you know that? Well, look at fluorine. It's on the periodic table. It's in group 7. All group 7 elements have the same number of valence electrons. Fluorine, chlorine, bromine, iodine. 7 valence electrons. So I have a total of 21 valence electrons. Add them up, 4, 5, 6. I got a total of 26 valence electrons coming from carbon, hydrogen, and fluoride, okay? Which to me now represents 13 pair. All right, so now I got to put them all together to see if I can come up with a structure. Carbon is the central atom. Everything else that follows is bonded to the central atom. So hydrogen's bonded to the central atom. I can simply draw a line in the H. And the 3 fluorides are also bonded to the central atom. I can very quickly put them up as follows. Okay. That took care of 4 pair. Everybody see that? That took care of 4 pair, leaving me with 9 pair to put someplace. Okay. Now, can I put any more around hydrogen? Can I put any more electrons around hydrogen? And can I put those 9 electrons around hydrogen?
No.
No, right? Remember, hydrogen is a duet. It's happy with just 1 pair. It's got 1 pair. It's done. Okay, in fact, that's something to tell you. If you ever see hydrogens, you put a line on it, it's done. No more, I can't add anymore. What about the carbon? Can I add any more to the carbon?
No, because it already has 8, right?
You got it, exactly. It's got 4 bonded around a carbon. So what is the logical place I got 9 of them. I can't just leave them alone. Where must they go? They have to go on the fluorides. Okay, that's the only place they can go. Okay, so I'm just going to start on 1. So here you go. 1, 2, and 3. Okay, the pair of the 3 pair. 6. Can I put any more on the far left fluoride? No, because there's 4 pairs around it already. Okay, I can't add any more. So I got to move to the next fluoride. So I do 3 again. 1, 2, and 3. That took care of another 3. So I got 3 pairs to work with. I can't add any more to that one because it's full with 4 electrons are out, 4 pair around it. And so the other 3 must go on the last fluoride. Now you go double check, make sure you didn't lose your 13 pair you began with, because it's feasible when you get a large number that as you're drawing and making lines, you end up losing a line someplace. So double check, we're at 6 around the fluorides, 6, 7, 8, 9, 12. What did I miss here? 9, excuse me, 9 around the fluorides, 9, 10, 11, 12, and 13. So no, that number checks out. Okay. So I got 13 pairs that accounts for all 26 valence electrons I started off with. And so I'm done. Now I got to figure out the general formula. A is always there. What would B be? And what would B be here? How many atoms are bonded around the carbon?
4.
It's 4. Do we have an E? No E. No lone pair. Now, if you inadvertently add a line to this, let's say you did that scenario, but you got to look at it. Now you got 2, 4, 6, 8, 10 electrons around carbon. Totally violates the octet rule. Okay, so now I've been asked the question, can you ever violate the octet rule? And that the answer is yes, but not for Chem 130. Okay. The Chem 130 where the octet rule is stable. We've got more advanced classes that, you can see, we can give examples where the octet seems to be violated, but you got bigger atoms to work with. But for us, 130 octet or duet, not violated. You got to maintain that. All right, so now we got the general formula AB4. Now we slip over, pick out the shapes table. We look for AB4, and that's the one we talked about earlier, where we had the most common configuration, tetrahedral, and that's the bond angle 109.5. So that is the tetrahedral for that fluorinated hydrocarbon. That is the geometry, and that is the shape for that particular compound. Okay. And all this information we're gathering from the valence electrons in this table. All right, back, and then we can see here that we came up with that. Okay. All right. Oh, I gotta stop for 1 second. I gotta stop something. So give me 3 minutes. Thank you. My apologies. I had to take care of this real quick. All right. So that is a general formula. We just got it. Notice that there's no lone pair on the carbon. Okay. Always 8. The magical number is 8. Okay. Everybody's got to have 8 electrons around it, except hydrogen. Hydrogen, you notice that one electron. Excuse me. All right. The next one, carbon dioxide, very interesting. We're going to come back to carbon dioxide down the road because it has a very interesting property. All right, here we go. So carbon, as we talked before, 1 carbon has 4 valence electrons, 4 electrons. Oxygen, okay, we have 2 oxygens. Now, how many valence electrons does each oxygen bring to the table? How many valence electrons does oxygen have?
6?
You got it. It's in group 6. So we got 12 coming from both oxygen. That's another error that possibly can happen, is you don't account for the fact that you got 2 of them. So you got to double the number of valence electrons, okay? Like we did with fluorine, we had 3 fluorines. We have to multiply it 3 times 7. So therefore, we have a total of 16 valence electrons, or 8 pair. Okay. Carbon is the central atom. And so we can put carbon in the central atom. The 2 hydrogens are bonded to the central atom. So we can very quickly write 2 lines, representing 2 bonds. And that took care of 2 bonds. So now we have 6 pair to put someplace. And I like to start from the outside, work my way in. So you can put them on the carbon as you want, put as many on carbon or to any other oxygen. But I find it, for me, to put them on the outside atoms and work my way in. So I got 6. So I'm going to go 1, 2, 3, 4, 5, and 6. Double check. That took care of my 6. I got 0 pair now. Okay, I had 8 pair to work with. I still got 8 pair. Okay, and I might say, okay, I'm done. No, I'm not. I got to check the octet. So once you write the general initial formula, check the octet. If everybody's happy with the octet, then you are done. But at this point, it doesn't look that way, right? So you can see, are there 8 electrons around each oxygen? There's 3 of them not bonded, and there's 1 of them bonded with the carbon, right? Everybody see that? Now, how many electrons, as written, do you see around carbon? How many electrons or how many pairs?
4.
Okay, there's 4 electrons. That's correct. So again, like we did with the first one, HCN, we need to create double bonds. Okay, and I'm going to do that. I'm going to speed it up a little bit because we're running a little bit behind. I'm going to create a double bond there. I just draw an arrow. I'm going to take that pair of electrons and create a double bond. Okay, that results in this type of structure. Okay. Do a double check, make sure I still have 8 pair. I got 1, 2, 3, 4, 5, 6, 7, and 8. I still have 8 pair. Okay. Now it may look magical, thinking that if I make a double bond, I'm losing them or I'm bringing in more electrons. I'm not. I still got 8 pair. I'm just putting them in such a manner so they are being shared by 2 atoms. So that I need to create either a double bond or a triple bond, just like we did up here in the first one. And so that is the final structure that we have. Okay. Our general formula, who can determine what the general formula will be for carbon dioxide? What do you think it will be? I got to go to the shapes table. So what general formula would I utilize? Of course, A is there. What about B? How many B's? 2. It's oxygen, right? And how many E's? None. Right? No lone pair. So our general formula is AB2. There's 8 valence electrons around each oxygen, and there are 8 valence electrons around the carbon. So everybody's happy. I got 8 pair. I didn't lose anything along the way. My general formula is AB2. And with that, I take it to the shapes table. And I get AB2, which is very similar to the HCN formula. Okay. That geometry is very important. We're going to learn that one would think that this thing is soluble in water, for multiple reasons, but it's not. It will dissolve in water, but it's not soluble, because if it was soluble, if you had a soda pop and you shook it, it would fizzle out. Okay. So anyway, we'll come back to that. And then finally, I got one last one, and we're going to stop it there. Okay, so that's the formula. Okay. Carbon dioxide. Remember, those dots represent, each one is an electron. You can write them as a dot, or you can write them as a line. All right, then we have NH3. And so we got nitrogen. Just write it over there, nitrogen. We got one of them. How many valence electrons does nitrogen have? How many valence electrons is 5? Exactly. It is in group 5, so there's 5 valence electrons. We know that the hydrogens each bring 1, but there's 3 of them, and so we got 3 valence electrons from the 3 hydrogens. So we have a total of 8 again, or 4 pair. Okay, 4 pair. Nitrogen is the central atom, so we can place nitrogen there. And there's 3 hydrogens bonded to the central atom, so we can very quickly draw a line. Okay, and that takes care of 3 of the 4 pair that we have. We got 1 pair. And as we talked about, hydrogens are happy. We can't add any more to the hydrogens because they're divided. So the only place that 1 pair left has to go is on the central atom, nitrogen. Okay, and so I double check. I still got 4 pair. Okay, and I got 3 bonded pair, and guess what? 1 non-bonded pair. So my general formula becomes A, B3, because there's 3 hydrogens, and now we got an E. Because that E, remember, represents the number of electrons, pairs of electrons on the central atom. Like here, these are lone pairs on fluorine, but we don't care about them because they are not the central atom. Okay. Same thing with oxygen. Oxygen has lone pairs here, but we don't care about them because they're not the central atoms. E represents the lone pairs on the central atom, just like it is here in ammonia. So our general formula is AB3E. And so that takes us to the shapes table again. And then finally, we look for AB3E. And there it is right here. Here's the general formula. And here is the structure. And it's all a little special name called trigonopyramid. Okay, and that bond angle between the hydrogens has been reduced. And the reason it's been reduced is because those lone pairs here's this nitrogen, this is hydrogen, hydrogen, and hydrogen. Those lone pairs on the nitrogen, that's what this kind of represents, like an orbital that's sticking up from the central atom with those 2 electrons. Remember, those 2 electrons are negative charge. They're going to repel each other. And when they repel each other, they're going to start, and they take up a lot of space up here, and they're going to repel these electrons, and it's going to shove everything down, okay? Resulting in a bond angle that its standard angle would have been 109, but now it's less than 109 because those lone pair push those electrons down. The same is true right here. It's a molecule. This represents water. Water has these 2 lone pairs, and that bond angle really shoved. You know, the result of that is we end up with a type of compound that we call polar. We got covalent compounds. Okay, 2 bonds, 2 types of compounds based on their bonding: ionic and covalent. Okay. Metal, non-metal combination, non-metal, non-metal combination for covalent. Now, as a subgroup of the covalent compounds, we have two types of covalent compounds. One's called polar and one's called nonpolar. And the best analogy for that is either something like water-like, which is polar, and something that's non-water-like or non-polar, like oil. Okay. And what do we know about those two? They don't mix. They don't mix at all. And but more on those properties later on. But it's all related to the structure of these molecules. And again, through the valence electrons that were involved in making those compounds. And that's the formula. So that is ammonia, NH3. Okay. All right, this is a rehash of HCM. We talked about carbon as a central atom. We added up the valence electrons, total them up. We have ended up with 5 pair. 1 pair equals 2 electrons. And then we started drawing the formula. We know that carbon was a central atom. We can make a line to represent the hydrogen and the nitrogen. Keep track of our pairs. We've got 5 pairs of electrons. We're going to check the octet. All right, so here we put in all the electrons that we had to begin with, 5 pair. Then we double check, we created double and triple bond because the octet of the carbon was not fulfilled, so we needed to borrow from Peter to share with Paul, so to speak, and create a double bond and or a triple bond until everybody's octet was fulfilled. But not with hydrogen. I can't overemphasize that with hydrogen because I get so many times examples of compounds with multiple bonds on hydrogen. Okay, but you can't because it's a duet. It's only it can only handle 2 electrons, and its orbital is 1s2. Okay, when it's maxed out, and to go any higher just requires too much energy. It requires to go on the second energy level, which is energetically not favored. Okay, so the next part, we're still going to continue with Lewis dot structures, but we're going to now work with what are called polyatomic ions. I'm not going to do any this time, but I will on Tuesday, but I want to share with you the periodic table. I know it's that thing I point to quite a bit. I stated in the beginning of the semester. I pointed out countless of times. All right, so on the periodic table, on the far left corner, there is a table called most common polyatomic ions. Right now, what these are units. These are groups of atoms that came together with a certain ratio, but are still ions because they have a charge, even though they are covalent. Like for example, NO3, it has a charge in it. It's an overall ion, so it has a negative charge. NO3 is that first one there. Right here, nitrate. Okay, and so we have these polyatomic ions, and we do have one cation, which is the ammonium ion, but most of them are negative. Okay, now they all have a charge, but we can also come up with a structure for these guys like we just did. The only difference is they're either going to have a negative charge or a positive charge. And depending on the charge means that in the final valence electron count, we're either going to subtract 1 or 2 depending on the charge. And then we proceed like we normally would, and we add another step or 2. Okay, but we will be using these polyatomic ions quite a bit on the road. So this is introduction to them. You already are familiar with a lot of these at home. This one that I've highlighted, it's called hydrogen carbonate. It's also known as bicarb. So sodium bicarb, potassium bicarb, magnesium bicarb, copper bicarb, sodium bicarb, aka baking soda. Okay, so you use that, and let's see some other ones. Hydroxide. I'm sure if you ever used not Drano, but liquid plumber at home to unclog your drains, you did use some sodium hydroxide. Yeah. And we tend to eat a lot of these sulfates or preservatives. There's all kinds of chemicals in your food. Okay. So let's stop it here, and we will continue with this part next time. And let me go make sure. Let's